Hi, this is Ms. Warnow. This is Matter and Change, Unit 1. Measurement and calculations will be the focus for this unit. Science is all about observing and experimenting. We need a way to add relevance to our observations and experiments, so we use measurements to collect and express our results. We have two types of measurements. We have quantitative measurement, which deals with a numeric value, such as the temperature reached 100 degrees. You can see the numeric value there. And then a qualitative measurement which does not deal with numeric value, such as the test tube felt warm. Quantitative measurements have both a magnitude and a unit, and both are equally important in this class. All of your measurements and numbers should have units. You can encounter large and small numbers in this unit, so you need to be able to convert to scientific notation. So starting out here, the number of 56,000, the first thing you want to do is move your decimal so that there is one non-zero digit to the left, so that would be 5.6, and then you're going to write times 10, and then you're going to count how many decimal places you moved. 1, 2, 3, 4. And then the last thing is you need to decide if that exponent is going to be negative or positive. And the way to determine that is you look at the original number. If it's greater than 1, it will be positive, and in this case it is. The next one, move your decimal so there's one number to the left, and do times 10, and then count how many places you moved it. 1, 2. And then decide whether this exponent gets a negative or a positive. And in this case, this number is less than 1, so you put a negative on there. Sometimes you're given the number in scientific notation, and then you have to write it in ordinary or standard notation. So the exponent will tell you how many places to move the decimal, and the sign on the exponent will tell you which direction. So since that's 5, it means we're going to be moving the decimal 5 places. It's positive, so we're going to move it 5 places to the right. So that's going to be 1, 2, 3, 4, 5. The next one, looking at that exponent, it's a -3. That lets us know the negative, that we're going to be moving it to the left. The 3 means move it 3 places to the left. So we go 1, 2, 3. 1, 2, 3. Check that. A unit tells us what was measured. The units must always follow the numeric portion of a measurement. And really there's two major systems. You have the United States customary system, which you probably know from everyday life, pounds, gallons, inches. And then we have what we call the SI unit, which is what all the other countries use. And we will be using SI units in this class. So make sure your units are SI units. And here's just a brief little physical quantities measured, letting you know what their base unit are. You have the mole. This is going to be very important later. The meter, kilogram, second, Kelvin, and then the ampere and candela you'll get to a little bit later in physics. So the metric prefix is based on powers of 10. You can look at this chart. You see it goes up in powers of 10 each time. Right, and so you need to have what's in red here memorized. You need to know the prefix for kilo, its symbol, and what it means. Hecto, deca, deci, centi, and milli. Okay, and this is just a little way for you to remember the order King Henry danced before drinking chocolate milk. You have to be able to write the equivalence between two particular units. So I'm going to go over this, work a few of these examples with you. Now this method here of putting a 1 in front of the larger unit and counting the number of metric places moved to get the desired unit only works for those places in this red little block here, because if you look closely, once you get out of the block, they're not going in increments of 10, they actually go higher than that. So looking at number 1 between meter and centimeter, a meter is the largest, so you put a 1 in front of it, and then you can just count here if you're at the meter and you're going to go to centimeter, 1, 2, so 1, 2, 100 centimeters. The largest unit out of a meter and a decimeter would be a meter. And then you come over here, you're trying to get to decimeter. You're going to move 1 spot. Get decimeter here. Number 3, a meter and a millimeter. So a meter is the largest, and it would take 1,000 millimeters are in 1 meter. And then for number 4, grams to megagrams. Now notice that megagrams is outside of that box. 1 megagram is going to be equal to 1 times 10 to the 6 grams. Okay. So take a moment and do 5 through 9 on your own. Pause the video and check that. All right, and here are those answers for you. You can pause the video and check those answers. All right, derived units are what we get when we take units and we multiply or divide them. So a common one would be volume. You know, from math class, you can calculate volume by saying length times width times height. And when you do a centimeter times a centimeter times a centimeter, you get centimeters cubed. Now, if we looked at a cube that measured 1 centimeter by 1 centimeter by 1 centimeter, and we multiplied that, we would get 1 centimeter cubed. If we put a volume of water in that, the amount of water it would hold would be 1 milliliter. This is an important relationship. We expect you to know that 1 milliliter is equal to 1 cubic centimeter. Density is also a derived unit. We get density by dividing the mass by the volume. And so when we do that, our density unit is always whatever the mass unit is divided by the volume unit. So we have grams per cubic centimeter, we could have grams per milliliter, we could have grams per liter for gases. If you've ever measured something several times, you know that the results can vary. And so in science, for a reported measurement to be useful, there needs to be some indication of its reliability. And so we have the terms accuracy and precision, and we expect you to know their difference. Accuracy is just how close the measurements are to the accepted value or to the right answer, the correctness. Precision is dealing with, if you made the same measurement multiple times, how close are they to each other? So the reproducibility of the measurement. So here, if you would give you what the accepted answer is and give you some measurements, you should be able to tell us if it's accurate, precise, both, or neither. Move this out of the way. And so for this measurement, it's precise. The measurements are actually close to each other, but they're not close to the accepted value. For this next one, you look at the measurements, and then you can look at the accepted value, and so you will see that they're precise because the measurements are close to each other. They're accurate because they're close to the accepted answer. On this one, here's the correct answer, the accepted answer, and here are the various measurements made. So for this one, it's neither. These numbers are not close to each other, these measurements, and nor are they close to the correct answer. Percent error is a calculation we use to decide to compare the expected results with the accepted results, or the theoretical to the accepted value. Notice these signs here. This indicates absolute value, which means when you subtract, you're always going to get a positive answer. So it says calculate the percent error in a length of measurement that is 4.25 centimeters if the correct value is 4.08. So we'd need to do 4.08 minus the experimental. Take that absolute value, divide it by the accepted, multiply by 100, and you should get 4.17. When we make measurements, due to human error, measurements always contain a degree of uncertainty. When recording measurements from equipment, it's important to record answers to the correct number of significant, to the correct number of figures. A measurement should include all certain digits and one uncertain digit. The certain digits are determined by the calibrations. We call those increments or intervals on your tool. So we have here, we have 2 rulers, okay, and we have a piece of wood or some object here, and we'd like for you to tell us what that measurement is. And so according to the first ruler, we can see an increment of 1 here, and so we go out to 4, but we need to read one place past it. So if I had to estimate that, this mark here, I'd say that's about 4.8 centimeters. The increments are in ones, and we carried out one place past. On this tool, you get a little more precision in the measurement. It's still up to 4.08 point, but we have these increments here. 1, 2, 3, 4, 5, 6, 7, 8. So we know it all the way out to 8. But you notice there it's a little bit in between that 8 and that 9th tick mark. And I would estimate that at 4.82 centimeters. So this one shows more precision. You get a more exact answer. Reading thermometers, you do that same way. So if we look on here, we have 80, 81, 82, 83, 84, 85, 86, 87. So we know 87 for sure, but we have to carry it one place past that. And so it's right here. It's kind of in between there. I think that's about 0.4. 0 degrees Celsius. On this next thermometer is 30, 31, 32, 33, 34, 35. It looks to me like it's exactly on that line. Well, we have to, since every interval is a 1, we still have to have that uncertain digit there. And since it's exactly on it, we'll call that 0, so 35.0. These are graduated cylinders here. Here's a picture. We use this to measure volume. And anytime you're reading a liquid, liquids form a curve, and then we call that the meniscus. And when reading a graduated cylinder, we always read from the bottom of the meniscus. So we're reading this one with 30, 31, 32, 33, 34, 35, 36. So it's going up in increments of 1, 36 point. So we need to carry that out to that next digit, 36 point. I would say that's 0.6 here. On this next one, 30, 31, 32, 33, 34, 35. It looks like we know it to the 1 spot. We have to estimate 1 past it. It's exactly on that line, so we'll put a 0 there. Call that milliliters. This is a burette. This is our most precise tool that we have. Just to show you a comparison, a beaker measures within 1 milliliter, a graduated cylinder within a tenth, but a burette measures within 100. Okay, so let me just move this down a little bit here. So graduated cylinder, if you're reading this, looks like it's about 91.7. But notice on a burette, it's not reading up because a burette actually is measuring what the volume that has left. So we actually read it from the top. So 46.123, 46.3 is what you know for certain, and you have to estimate that last digit. That's an estimated digit. Okay. There's another burette here. We're still going to read from the bottom of the meniscus. But notice that since this is a burette, it's reading down 6.1, 2, 3, 4, 5, 6. That's the 6.6, and then they're estimating that to be 3 mils. On this one, read from the bottom of this meniscus here. Oops, I went a little bit low, but 20. 0.123, say 20.3, and it's right just a little bit above that 4 tenths, so I'm going to put that as a 9 here, 20.39. Notice that you're reading it differently from a graduated cylinder. And then for a triple beam balance, what you do for a triple beam balance is we add up all the beams. And so that's going to be 500 plus 35, 30, and you have the 6 here, point, and we have to look real closely at this, 6.1, 2, 3, 4, 5, 6, 7, 8. And it looks to me like it's exactly on the 8. Well, since it measures increment-wise all the way out to the 10th, we have to put something in the 100 spot. Since it's exactly on that line, I'm going to put a 0 there to indicate that. Now, what about digital equipment where you can't see these intervals? Well, on a digital equipment, you should record exactly what you see. So on this scale, this balance, you would record 12.68. On this one, it looks like it's 31.7. There is no estimating on a digital balance, or digital equipment, record exactly what you see. This concludes video 1. Make sure you've taken good notes. Come to class with any questions. I hope you have a good evening.